In this series of videos I'm attempting to repair this Televideo TS800A dumb terminal and computer combination. So what we have is a 6502 computer system running the dumb terminal, and then on the right here we have a Z80 running the computer side. The two are almost completely independent. There's a serial link between the two of them, and they do of course share the power supply, but other than that they are fairly independent. The previous video we went through using the logic analyzer and we found a fault with the CTC chip. The Z80 was trying to program it to generate an interrupt, but the interrupt was never thrown, and so the self-test that was testing that device failed. So we got as far as LED 3 was coming on and then flashing to indicate that that test step was failing. So I have now fitted a replacement CTC. Before we see what now happens, just a quick mention that I posted a video about how to decompile the code that we were looking at for the Z80. A couple of comments on there. I just want to address that the commenter said that you can get software to do this, or at least to help with this process, and you can and you can't. You can get software. If all you want to do is decompile the software and examine it, have a look through it, then yes, there are plenty of programs you can use to do that. I find the process I showed just as easy, just as quick, and it's the method I prefer. However, the process I showed, I use that method because what we're trying to do here is not really just decompile the code. What we're trying to do is repair this machine, and because of that we are trying to repair a hardware fault. We're not really trying to repair the software. The only reason we're decompiling the software is so that we can see what the logic analyzer is picking up and what the system is doing. Now you can't really do that within a software environment because it won't know anything about the hardware that you're running on. You can usually set them up to provide what amounts to hardware inputs, but to be able to simulate the fault we're seeing on the machine, you would need to know what's causing the fault, and if you know what's causing the fault, you don't need to be searching for it. So the method I showed is I've kind of developed it over time for good reason. It's a very good way of looking at the code, decompiling it, and then using the logic analyzer to find out what the hardware is doing. It's a very quick and easy process, and it's not overly cumbersome to do. It might look complicated, but once you've done it a few times it's quite straightforward. It's also quite a bit of fun, and it's a good way of learning how the machine works, and if you're not familiar with the processes, it's also a very good way of learning about the processes. So as I said, I've plugged in a new CTC chip and we'll see if the test gets any further. Incidentally, I was asked why I suspect the CTC chip. Just because the interrupt's not being thrown, it could have been something else, and that's very true. It could have been anything else interfering with the interrupt. The only reason I suspect the CTC is because the first thing I did when it failed the test was pop it out the board, put it into the IC tester, and it failed the test. So even if there are other faults, we need to put a new CTC in because the one that was in there wasn't working. So we'll see if we get any further. Remember, it was getting to the third LED, and then it was just flashing that LED to indicate that the interrupt that the CTC was supposed to throw never occurred. So okay, we'll get this powered up. So that's the RAM self-test LED. It will then go on to DMA, and it's definitely getting further this time. So you saw, I'll just repeat the test. I'll power it off, back on again. So that's the RAM test. Next LED's DMA, then the CTC, and I believe this double flash is one of the SIOs. I think it's the second SIO test has failed. But what we'll do before we look into that is we'll go back to the logic analyzer just to kind of tie up the loose ends. We'll try and trap the logic analyzer on the interrupt as we did previously. Remember, the interrupt was never being hit before, and we'll see if we're now getting the interrupt, and that will just confirm that what we'd kind of deciphered from the software is actually what's happening. As I said, it's a good way of learning, and I always like to just confirm that any assumptions I made were correct because it helps in the next repair. So I'll move the camera, we'll have a look at the logic analyzer, and we'll try and trigger on the interrupt and see if we are getting there this time. If you recall, the interrupt was at address 37E, so we'll enter that as our trigger point. And so if we get to that address, then we know the interrupt occurred, or something has gone badly wrong with the rest of the software. So I will now arm the analyzer, turn the machine off and back on. It's now off, turn it on, take a few seconds to go through the first few tests, and then we'll see if we manage to trigger on the interrupt. And we have indeed triggered, and as you can see, we're at 37E, so the interrupt is now occurring. Kind of suspected it was because the test is going further, but what we need to do now is see why the next test step is failing. Exactly the same process as last time. What we're going to do now, because we've got to the point the two LEDs are flashing again, and so we've got to the point in the code where the error has occurred. So we'll now be in the same loop that we were in before. The two LEDs are flashing, but the LEDs flashing are in the loop that shows the error code. If you remember, there was a loop that turns the LEDs on and off, and the way that function works is it's the LEDs that are required to flash are supplied in the A register, and then it just flashes those LEDs on and off until you turn the machine off. So we need to find out what is now calling that function. So if we just get rid of the trigger completely, and we'll just run and confirm our suspicions, make sure we are in that bit of code, and indeed we are. We can see, you might remember it from the previous video, that the address was 544, 545, etc. So it is that loop where we are flashing the LEDs. So what we need to do now is just find out where this was called from, and so what I'm going to do is trigger on 544, and then we can backtrack and see where this function was called from. Okay, now we will of course need to reset the machine in order to get to this particular address, otherwise we'll never actually get there. So we'll turn that on. It's going through the self-test, and it's now got to the point where the test has failed. So we can now go backwards through the code and find out exactly where this function was called from this time. And so what we're looking for here is an entry on the stack, and that's what we have here. So anything prior to these values, these are the stack values at the moment, or they're in the stack area, so we can probably assume these are the stack usage in response to a call, and so it's the address just prior to that we are interested in. So yeah, we're looking at address 58E up to 590, that sort of area. So I'll have a quick look. I won't show you the source code again, it's probably getting fairly boring keep looking at that, but I'll go and have a look and try and figure out where we are. Most likely it's a failure of the SIO test, but we'll have a look and see what we find. So the block of code this comes from, all it's really doing is sending some data out of the serial port. So we need to go back to the beginning of that block, and you can see all we're doing here is just tracking our way back through the code, looking for why a self-test would have failed. And nothing we've looked at so far is the reason for a self-test failure. So we'll go back. The beginning of this block of code is at address 7cc, so we can change this once again. Restart the machine. Wait for the self-test to get to the point where it fails, which is there. And once again we can jump back through, and again we see a call here. And so what we'll do is go back, and as you can see the address we're interested in is 42B, 42C, around that area. So I'll go and see what that block of code is up to. So unsurprisingly it looks like we have an issue with one of the SIOs. So what I'm going to do now is try swapping out SIO2. The reason I'm going to start with that one is because the two flashing LEDs I believe are a result of the failure of SIO2. So combining that with what we're looking at on the logic analyzer would seem to make the most sense. So I'll go and get a replacement SIO, we'll plug that in and see if we get any further. I fitted a new SIO chip, and the one I took out I tested and it is indeed faulty, so that can be put to one side. And let's get this out of the way so we can see the board. So I also replaced the line driver and line receiver ICs for that channel on the SIO. They were both getting very hot, so I took those out, tested them, and indeed they have both failed as well. So I've taken those out and replaced them, put the new ones in sockets of course. So we're now ready to boot this back up and see if we get any further through the self-test. So that's the RAM test. So we're now still getting the same error indication. So what I'm going to do is reattach the logic analyzer, see if it's failing in the same position, the same point in the code, and we'll go from there. I won't bother showing you the logic analyzer. If that's the sort of thing you want to see more of, then leave a comment, but all I'm going to do is see if it's failing in the same place. So I run the machine up and it is failing in the same place, the same test. I also searched through the source code, and you may recall that the function that displays the error, the one that flashes these LEDs, it's just a loop with some delays in it, and it takes the value supplied to it in the A register and it uses that to determine which of the LEDs to flash on and off. And in this case it's been supplied with a value of 3. So that means that the first and the second LEDs are the ones that will flash. And what I did is search through the source code looking for any other tests that use the same value before calling that function. And there are 4 separate tests that will flash the same 2 LEDs. So there are a number of duplications in the fault diagnosis. It's also a bit strange in that it kind of jumps between the 2 SIOs. It uses the one that's currently failing earlier in the test sequence, not as part of a test but to send data to the 6502. So a bit of an odd sequence, but I've popped the SIO back out and tested it, and it tests fine, but we're still failing in the same point. So I suspect there is something else going on with it. Like I said, the line driver and line receiver for that particular device weren't working, so it looks like it might have had a major issue with that particular device. And so what we'll do now is start investigating it, and because we've got as far as we can with the logic analyzer, what it's doing is loading some values into the transmit buffer of the SIO, and then it's waiting for the transmit to complete. So what it does, what the entire test loop does in that part of the test, it checks to make sure the device is ready. If it's not, because it should be after a boot up or reset, if it's not ready, it flags an error, flashes the 2 LEDs. If it is ready, it loads some values into the buffer, and then it waits for a short time, long enough for that data to have been sent out of the serial port, and it then rechecks to make sure that the transmit register is once again available. In other words, that it has successfully sent the values. But it's failing at the second of those 2 test steps. It's loading the values fine, but when it's waited for the data to be sent and come back to make sure it's been sent, the unit or the device has not flagged that it's successfully sent the data. Now it is possible that there's something wrong, maybe it's waiting, it's been told to wait to send. There are of course hardware handshaking options for this, but in the mode it's running in, now I've checked the dip switches, the mode it's running in, it should just send the data. And I have used the scope just to check those pins, and they are in the correct mode, so in theory it should be sending the data, and it's not. So what we'll do is grab the schematic, we'll find the correct page for that particular device, and then we'll just scope it out and see what's not working. So just find the relevant page in the schematics, and so this is the correct page. So as I mentioned previously, we have 4 channels, 2 channels for each of the SIOs, and the one we're interested in here is channel B on this one. This is where the test is currently failing, so it's waiting for the transmit register or transmit flag to indicate that the transmit register is empty. And so I've replaced these 2 devices already, so I know they're working. So for some reason this doesn't appear to be sending the data. We know that the rest of the system in theory is fine, all things being equal. The Z80 can write to and read from this device. And this connection here, it is there, it shows it's being cut here. It's the same one over here that's cut. It's obviously they're using it in a slightly different way to the original design. This is not being cut, but that should not stop it from sending the data. So something else is going on with this, and the first thing I've checked is the voltages, and they're fine. So the next thing we'll do is start probing around this. Each of the 2 channels has got a separate clock for transmit and receive, so there are 4 clocks that go to this. And in this case they're actually connected together, so it's using the same clock for transmit and receive for port B as it is for port A. So we'll check these. We'll start with A. So we're looking at pins 13 and 14, and we should see a clock on those pins. So power the machine up, wait for the self-test to finish. Okay, so we'll check pins 13 and 14. Pin 14, pin 13, so we're not getting a clock on that one. We'll test the clock pins on the second channel. So that's these 2 pins, and they're pins 27 and 28. So we'll check those pins. And no clock there either. We'll just check it on the other of the SIOs. And as you can see on that device we're getting a clock. These are separate clocks, they're not supplied from the same source because they run at different frequencies. But you can see that we should be getting a clock there. We're not getting a clock to either of the channels on that device. So we'll follow just one of these back. Goes back to sheet 9. It says baud rate printer, so we'll find sheet 9. Okay, so on sheet 9, okay, baud rate printer, so it comes from the CTC chip. The CTC, as well as being a timer, it also has some dividers in here, so you can use it to generate various clock signals, which is what it's been used for here. And we're not getting clocks on either of the first 2 lines, so that's channel 0 and 1, and each of those channels has its own separate clock input. And you can see, possibly, hopefully, that the clocks for channel 0 and 1 are tied together, so they're fed from a common clock, and that's on pin 22 and 23 of the CTC. So we'll check that. Okay, and we're not getting a clock on those pins. So clearly the clock is missing. That explains why the SIO can't send any data. It's not receiving a clock. If we trace this back, it comes from this device. This is A28. And this is just a simple 4-bit binary counter. And we are interested in pin 11. We'll find A28. Luckily these are in order. Just trying to see this, so it's that. So it's this pin, and pin 11. There's nothing at all. In fact, all 4 of these pins, 11, 12, 13 and 14, should have a clock. And there is nothing. So we'll see what is feeding a clock into that device, and it's coming from our main system clock generator. So we have the main system clock here It's feeding this divider, and this is what provides all the various clock signals the system uses. So we are interested in pin 2 of A28, that's where the clock should be coming in. We'll see if that's existing. We know the main clock's working because the Z8 is running, so it's very likely that there's something wrong around here somewhere. And indeed we are getting a clock going into that device. So clock going in, nothing coming out. I suspect this device is faulty, so I'll go and swap this out, and we'll try again and see if we can get any further. So I've replaced that counter, and it did indeed test as bad. Fitted a replacement, and so we'll check this when we power it up, and we should be getting a clock on this pin now. If you remember, we weren't getting anything on here, and we can also keep an eye on the LEDs and see if we get any further through the test. So I'll power this up. We are now getting a clock, so that's a good sign. See if we get any further through the self-test, and it appears to have got all the way through. When all the lights, all the LEDs go out, it's completed the self-test. So we'll try that one more time. That's a RAM test. Okay, so it's gone all the way through the self-test. That most likely means the Z80 is running. And one thing we can test now, we weren't getting anything out of the port that goes to the monitor previously. We should be getting the two sync pulses and the video out. So what we can do now is see if we're getting anything at all on those pins. So we'll try the first one. Okay, so we are getting 28 kilohertz pulses on this one. 87 hertz on that one, so that's looking very promising indeed. Just going to restart this. I'm just going to turn up the scope gain a bit, see if we're getting any video. I'm not seeing a great deal on the video out. There does appear to be something, but hard to say exactly what's on there. So there are pull-up resistors on the video board, so it may be that it's not going to show us any video until we plug the monitor in. But we are now getting the sync pulses. And that means that the 6502 is now actually up and running as far as driving the video out is concerned. That comes from the 6502 side. The Z80 does seem to be getting all the way through the self-test. Doesn't mean it's fully operational, of course, but what we'll do in the next video is we'll connect up the monitor and see what the unit's now actually doing. Keyboard's not plugged in yet. I don't know if it will actually boot up without that in. Keyboard doesn't work at the moment, it's in a very poor condition, and that's something that I will need to get sorted out. But as I say, in the next video we'll get this connected to the monitor and see how far it now gets.